right, in chapter 1, what we studied was what is a digital signal and the difference between a digital signal and an analog signal, etc. So we came up with some of the basic terminology from the history and some other stuff. So basically on this, what I wanted to do is show you a couple ways we actually create a digital signal. As you can see on the screen right here, I have an oscilloscope. This is multisim, so I've used oscilloscope. Yes, you can pick up multisim for student copy for, I think, around $35, $40. So you can talk to me in class about it. But basically what I have done here, I got my function generator, which is right here. And then I have my oscilloscope, which is down here, similar to what oscilloscope we use in class. So what we actually have done here is I set up the oscilloscope to look at the function generator. I set this function generator for 1 kHz and 2.5 volts peak. Well, let's look at this 2.5 volts peak first right here. See this right here? This line right here? This is our ground line because there's an arrow right there. That arrow right there is the ground line. And then if you go straight across, so if we actually go up, well, each one of my divisions, see channel 1 is 2 volts down here. Each one of these divisions, that's a division, that's a division, that's a division, etc. And these are subdivisions right here. And it gets a little tricky when you have to start using, you have to break up the subdivisions, but that shouldn't be too hard. So if we look at this, this is going up here as a peak. So we got 2.5, we got 2.5 right here because that's 2. And then each one of these is about 2, 4, 6, 8. That's about, let's see, 2, yeah, that's about 2.5 right there. And if we look back down here, that's 2.5. So if we look at this thing's actually giving us 2.5 volts peak. Well, it is. That's 2.5 volts peak and 2.5 volts peak. So this is 5 volts peak to peak right here. So from here to here is a peak to peak. From here to the ground line is a peak. From the ground line to here is a peak. So if you go from here to here, that's a peak to peak. So what I want to do is I'm going to spread this out just a little bit so I can actually show you how to get the frequency on here. Now, most of these oscilloscopes, you can measure it, and it does the measuring for you and does everything for you. But it's good to always verify and check to see what you actually have. So in this case, what we're actually doing, we're trying to find the frequency. Well, we know time goes across horizontally this way, amplitude's this way, so that's voltage, and this is time. So we're voltage over time. So on the time scale, what we want to do is we go from this point right here over to here is 1 period. So from here to here is 1 period. So if we count the number of divisions, again, this is going across vertically, 1, 2, 3, 4, 5, 5 divisions, and we multiply it by 200 microseconds. So we got 5 times 200, e to the minus 6. Well, it gives me 0.001. Well, if I take that 0.001, that's our time. That is actually 1 millisecond. So if we look at 1 millisecond, we inverse it. I do 1 divided the second answer. I should get 1 kHz, and I do. So basically, what you're doing here is you go straight across, and you count the number of divisions going across from 1 full cycle, or 1 full period. You get 1, 2, 3, 4, 5. And then you take this number, this microseconds down here, and you multiply it. 5 times 200 is 0.001 or 1 millisecond. And we inverse 1 millisecond gives 1 kHz. So that's pretty much how you could read the oscilloscope. Again, the voltage on here, again, if we use this ground line, there's 2.5. So it's 2.5 and 2.5, so it's 5 volts. Now, what if I change it? Watch what happens when I change it. So if I change it, let's say I go up to 3. So now let's take a look at what we have here. So we have each one of my divisions still is 2, and now we got 2.5. Well, that gets a little tricky. You know, I could say that's about, you know, we're supposed to be at approximately 3 volts peak, and there's 2, and there's 4 up here. So right in the middle becomes really close, but what I could do is change the division out here. So what I could do is change the divisions. There we go. And trying to get it down to, there we go, 1 volt. Sorry about that. Now we get it much better. So look at this. So each one, the ground lines here, 1, 2, 3, that's 3 volts. 1, 2, 3, that's 3 volts. Peak to peak is 6 volts. And I can actually change that on here if I want to, but I'm not going to. I can change the peak to peak. What about the frequency? Well, I can change the frequency on this function generator as well, but notice that the frequency did not change. I still have 1K hertz. So increasing the amplitude does not increase your frequency. To change the frequency, I can actually come over here and I can enter in, let's say, 2K hertz. Let's go 20K hertz. And we should have something that happens. There it goes. So I'm going to do my auto set here, and it's going to set me up. And I'm going to do as a time division, I'm going to increase it so I actually see it. I'm going to do some measurements to verify. So I'm going to do is move this guy over. There we go. Move this guy over. And now what we have is we count how many divisions. So we want one full cycle. So it's a full, let's call it a square. And then it starts off over here. So it's the rising edge to the rising edge. 1, 2, 3, 4, 5. 5 times 10 micro. So 10 e to the minus 6 times by 5. I get about almost about 0.5 microseconds. So if I take 1 divided into answer, I get 1 divided into second answer. I get 20K hertz. So that's how you would actually see. That's how you would use an oscilloscope. So let's go on to a different one. I'll show you a different circuit here. I'm going to close this guy out. So if I actually go on to a different circuit here, I'm going to run this one. This is what we call a 555 timer. This is what we call a virtual 555 timer. I'm going to scoot this over a little bit here. So basically what this thing set up is you have a voltage divider. Everybody's been asking where to use voltage dividers. Well, R1 and R2. That's a voltage divider. We have a 1K here and looks like a 1 mega ohm resistor right down here. 1000K looks like it is 1 meg. It's kind of high. That's really kind of high, but that's okay. I can deal with that. And then we got a capacitor. So this is actually you take the ratio of these R1 and R2 with this capacitor, you produce a waveform that looks like that. So if we can actually change the frequency on this, makes it go a little faster or makes it go a little slower. I can do what I want, so I go a little faster. What's important here is that I could, let's see, I'm going to go up and I'm going to take my my time and I'm going to, now I can do the measurements I want. I really don't know what the frequency on here is. You know, I could do the measurement, show you how to do that in a second, but you notice my light is lighting up, it's blinking. Great, nice, blinking light, wonderful. I'll talk about the circuit in a second here. But basically, if I want to know the frequency on here, there's two ways. I can actually measure it, or I could do the math like I did before. So in this case, I want to know what the frequency at 85% of this pot here, this potentiometer. So if I look at this and I do it, I count the number of divisions. So if I look at the rising edge to the rising edge, I have 1, 2, 3, 4, 4. There's 4. There's 5. So I got 4 point. I'm going to say 4.8. So if I take 4.8 times that by my 100 milliseconds, mil is 10 to the minus 3, and then I invert it. I get 2.08. I get 2.08 hertz. So that's almost a 2 hertz signal right there. That's not too bad. That's a little fast for a clock, but I can actually do is bring it down one. And I keep bringing it down. And I can bring it down to where I want it. And what's nice about this is that I can actually come here and I can actually get a frequency that's close to 1 hertz. And I will talk to you about the 555 timer in a second here. So there we go. So if I look at this and I now have 200 milliseconds, I go 1, 2, 3, 4, 5. Well, I need this guy to be a little bit more this way, so I can actually just keep adjusting here a little bit. And eventually you'll get it. So that gives you an idea what a digital signal looks like and how to read it on an oscilloscope. Thank you.